For thousands of years, moving water was one of humanity's most dependable allies. Rivers turned stones into flour, powered hammers in forges, and quietly drove the earliest machines long before steam or electricity existed. These humble water wheels, wooden, slow, and simple, laid the foundation for an energy revolution that still powers the modern world. Today, towering dams rise from river valleys, and turbines the size of houses spin with extraordinary force. Hydropower plants generate electricity for entire nations, stabilizing grids, supporting industry, and supplying renewable energy to hundreds of millions of people. What began as a wheel dipped into a stream has become one of the largest sources of clean power on Earth. This transformation did not happen overnight. It unfolded across centuries of engineering, necessity, and innovation through medieval mills, industrial factories, and the birth of electrical science. Each step refined humanity's ability to convert flowing water into useful work. How did simple water wheels evolve into massive hydropower giants? And how did this ancient technology become a cornerstone of modern energy systems? This is the story of how moving water shaped industry, electrified societies, and continues to drive the future of renewable power. Long before electricity grids and concrete dams, humanity learned to read the power of flowing water. Rivers were predictable, persistent, and free, an energy source that did not need to be burned or hunted. Early societies discovered that by redirecting water's motion, they could multiply human and animal labor, transforming survival economies into productive ones. The earliest water wheels appeared more than 2,000 years ago. In ancient Greece and Rome, simple vertical wheels were installed in streams to grind grain. These first designs were crude but effective. Paddles or blades caught the current, turning a central shaft connected to millstones. What mattered was not efficiency, but reliability. As long as water flowed, work continued. This principle, continuous mechanical power, would define water energy for centuries. Two basic concepts emerged early. Undershot wheels relied on fast-moving water striking paddles at the bottom of the wheel, common in flat regions with strong currents. Overshot wheels, developed later, used gravity instead of speed. Water was carried to the top of the wheel and poured over it, using weight to generate torque. Though slower, overshot wheels were far more efficient and became dominant in hilly and mountainous regions. By the medieval period, water wheels spread across Europe, the Middle East, and Asia. They powered flour mills, sawmills, textile fulling mills, and metalworking hammers. Entire villages formed around rivers because water power meant economic independence. In some regions, rivers were carefully engineered with channels, weirs, and mill races to maximize usable flow. This marked an important shift. Humans were no longer just using water, they were shaping landscapes to harness it. China developed parallel innovations. Large-scale water-powered bellows supplied air to blast furnaces, supporting early iron production. In the Islamic world, engineers refined gear systems and mechanical linkages, transferring rotary motion into complex tasks. Water power became not just a tool, but a mechanical language: rotation, gearing, transmission. Despite its success, water power had limitations. Wheels were location-bound, dependent on seasonal flow and geography. Droughts reduced output. Floods destroyed infrastructure. Power could not be easily transported. It had to be used where it was generated. As industries grew larger and more complex, these constraints became more apparent. Scientific understanding also lagged behind practice. Early builders relied on experience rather than theory. Concepts like energy, efficiency, and fluid dynamics were not yet formalized. Yet through trial and error, millwrights optimized designs, improving blade angles, materials, and gearing. Knowledge spread through apprenticeship rather than textbooks. By the 18th century, water wheels had become the backbone of pre-industrial economies. They powered workshops, supported early factories, and enabled mass production before steam engines dominated. Crucially, they proved a foundational idea: natural motion could be converted into mechanical work at scale. This idea, extracting continuous power from flowing water, was the conceptual bridge to modern hydropower. The tools were primitive, but the principle was sound. When science, metallurgy, and electricity finally converged, the water wheel would not disappear, it would evolve. The true transformation of water power began when engineers stopped thinking in terms of wheels and started thinking in terms of flow, pressure, and efficiency. The Industrial Revolution demanded more power, delivered more reliably, and in forms that could drive increasingly complex machinery. Simple wooden wheels, however ingenious, were reaching their practical limits. The spark that would turn ancient mills into modern hydropower came from a new way of understanding moving water in the late 18th and early 19th centuries. Advances in physics and engineering reframed water as an energy system rather than a mechanical helper. Scientists began formalizing concepts like energy conservation, torque, and fluid dynamics. This theoretical foundation allowed inventors to redesign how water interacted with machines. Instead of large, slow wheels exposed to the elements, engineers envisioned compact devices that could extract more power from the same volume of water. The breakthrough arrived with the development of the water turbine. Unlike traditional wheels, turbines enclosed and directed water through carefully shaped blades, converting kinetic and potential energy with far greater efficiency. In 1827, French engineer Benoît Fournerin built one of the first practical water turbines. His design achieved efficiencies far beyond any wheel, spinning at high speeds and delivering steady, controllable power. For the first time, water power could be scaled and standardized. Other innovators quickly followed. James B. Francis refined turbine design in the mid-19th century, creating the Francis turbine, a versatile system capable of operating across a wide range of water flows and heights. Its curved blades and inward flow configuration made it ideal for rivers and medium head installations. Around the same time, the Pelton wheel emerged for high-head, low-flow environments, using powerful water jets to strike spoon-shaped buckets. These designs proved that water power could be tailored to geography rather than constrained by it. The next decisive spark came with electricity. In the late 1800s, inventors realized that rotating turbines could drive generators, converting mechanical motion into electrical energy. This removed the greatest limitation of traditional water power: location. Electricity could be transmitted over wires, allowing energy generated at rivers and waterfalls to power cities miles away. One of the earliest demonstrations occurred in 1882, when a hydroelectric plant on the Fox River in Wisconsin supplied power to paper mills. Soon after, larger projects followed. In 1895, the Adams Power Plant at Niagara Falls began transmitting hydroelectric power over long distances, lighting streets and driving industry. The sight of a natural wonder producing electricity captured public imagination. Water power was no longer medieval, it was modern. These early hydroelectric plants faced enormous challenges. Engineers had to design turbines that could withstand immense forces, manage fluctuating water levels, and operate continuously. Materials science advanced rapidly, replacing wood with steel and cast iron. Control systems improved, allowing operators to regulate flow and output. Each problem solved pushed hydropower closer to industrial maturity. Public and industrial reaction was swift. Hydroelectricity was clean, reliable, and relatively cheap once infrastructure was built. Unlike coal-fired plants, it produced no smoke or fuel waste. Cities near rivers and waterfalls found themselves at a competitive advantage. Factories relocated. Urban electrification accelerated. Water, which had powered individual mills for centuries, was now powering entire regions. Crucially, these breakthroughs did not erase the past, they built upon it. The principles of rotation, gearing, and continuous flow learned from water wheels informed turbine design. The ancient idea remained intact, but the form had changed completely. By the dawn of the 20th century, the spark had fully ignited. Water power had crossed a threshold from local mechanical aid to centralized electrical generation. The stage was set for massive dams, continental power grids, and hydropower giants that would reshape landscapes and economies alike. The wheel had become a turbine, motion had become electricity, and an ancient force had entered the modern age. Once turbines and electricity proved that flowing water could power far more than local mills, hydropower entered a long ascent defined by scale, engineering, ambition, and national investment. What followed was a century-long transformation in which rivers were reshaped, technologies refined, and water power elevated into one of the pillars of modern energy systems. By the 1880s and 1890s, hydroelectric generation moved from experimental to practical. Early plants were modest, serving nearby factories or lighting systems. Yet even these small installations revealed a critical advantage. Water provided steady, predictable energy. Unlike steam engines that required constant fuel delivery, hydropower drew from a continuous natural source. As electrical transmission improved, distance between generation and use became less restrictive, allowing planners to think bigger. Niagara Falls became a proving ground. The Adams power plant demonstrated that massive natural flows could be harnessed and transmitted over long distances. This success legitimized hydropower as a serious alternative to coal and marked the beginning of large-scale infrastructure projects. The early 1900s saw governments recognize hydropower as a strategic asset. Large dams were built not only to generate electricity, but to control floods, support irrigation, and stimulate economic development. Concrete gravity dams and arch dams allowed engineers to store water, regulate flow, and generate power year-round. Projects such as the Hoover Dam in the United States symbolized this era. Completed in the 1930s, it demonstrated how engineering, policy, and energy could align on a national scale. Entire regions were electrified, cities expanded, industry flourished. Hydropower became a tool of modernization. At the same time, turbine technology advanced rapidly. Kaplan turbines were introduced for low-head, high-flow rivers, complementing Francis and Pelton designs. Hydropower systems became adaptable rather than uniform, optimized for local conditions. That is, electrical grids expanded. Hydropower plants were integrated into national and regional networks. Their ability to ramp power up or down quickly made them ideal for balancing supply and demand. Hydropower became not just a generator, but a stabilizer of energy systems. Post-war reconstruction and development drove global expansion. Europe rebuilt and modernized hydro facilities. The Soviet Union constructed vast projects across Siberia. Japan harnessed mountainous rivers. Developing nations viewed hydropower as a pathway to industrialization, reducing dependence on imported fuels. By the 1970s and 1980s, hydropower faced new scrutiny. Large dams altered ecosystems, displaced communities, and changed river dynamics. Environmental movements forced a reassessment of costs and benefits. In response, engineers improved fish passages, sediment management, and flow regulation. Smaller run-of-river projects gained attention as lower-impact alternatives. Technological optimization continued. Computer modeling improved turbine efficiency. Automation reduced operational risk. Aging plants were upgraded rather than replaced, extending lifespans and increasing output without new dams. Today, hydropower stands as the largest source of renewable electricity globally. Massive installations in China, South America, and Africa generate power on a continental scale. Pumped storage facilities act as energy batteries, storing excess power and releasing it when demand peaks, an essential function in grids increasingly supplied by solar and wind. Throughout this ascent, hydropower evolved from simple mechanical rotation to a sophisticated energy system. Rivers became reservoirs, wheels became turbines, local mills became national infrastructure. The ascent of hydropower reflects a broader human pattern, learning first to use nature, then to understand it, and finally to integrate it into complex technological systems. Flowing water never stopped moving. Humanity simply learned to move with it on a far grander scale than ever before. The moment hydropower moved from ambitious engineering projects into the daily functioning of societies, its impact became unmistakable. What had once powered individual mills or local factories now energized entire regions. Electricity from rivers flowed into homes, schools, hospitals, and industries, reshaping how people lived and how economies grew. Hydropower was no longer a niche, it became a foundation of modern life. One of the most profound shifts was electrification at scale. Hydropower enabled reliable, continuous electricity in places where coal was scarce or expensive. Rural regions, once isolated from industrial progress, gained access to power for lighting, refrigeration, and machinery. This reduced inequality between urban and rural areas and accelerated social development. Education improved as schools gained electricity. Healthcare advanced as hospitals could operate modern equipment. Daily life extended beyond daylight hours. Industry was transformed. Hydropower provided the stable energy needed for aluminum smelting, steel processing, chemical production, and manufacturing industries that demand large, constant power supplies. Entire industrial hubs grew around hydroelectric plants. In countries like Norway, Canada, and Brazil, hydropower became a competitive advantage, shaping national economic identity and export strength. Society's relationship with energy also changed psychologically. Electricity became expected something that should always be available, affordable, and clean. Unlike coal plants, hydropower produced no smoke-filled skies or fuel trains arriving daily. Energy felt quieter, more natural, almost invisible. This helped normalize the idea that large-scale power generation did not have to come with constant pollution. Governments embraced hydropower as a tool of national planning. Dams were built alongside irrigation systems, flood control infrastructure, and water management projects. Rivers became multi-purpose assets simultaneously supporting agriculture, energy, transportation, and urban growth. In many countries, hydropower projects symbolized progress, self-sufficiency, and technological capability. Yet the societal shift was not without cost. Large dams displaced communities, altered ecosystems, and submerged cultural heritage. These impacts sparked debates that reshaped public expectations. Citizens increasingly demanded that energy projects balance economic benefit with environmental and social responsibility. This pressure forced new standards, impact assessments, and community involvement, changing how large infrastructure projects were conceived and approved. Despite these tensions, hydropower's mainstream adoption proved enduring. It demonstrated that renewable energy could operate at national and continental scales. Long before climate change became a global concern, hydropower showed that clean electricity could power modern civilization. The revolution was not just technological, it was societal. Flowing water moved from background feature to central infrastructure, shaping where people lived, how they worked, and what they expected from energy itself. Hydropower did more than generate electricity. It redefined what progress could look like. In the contemporary era, hydropower has moved beyond sheer scale and into refinement, flexibility, and system-level importance. While the iconic image of massive concrete dams still defines public perception, modern hydropower is increasingly characterized by optimization, diversification, and integration with broader energy networks. Today's hydropower plants are far more efficient than their predecessors. Advances in computational modeling allow engineers to design turbine blades that extract maximum energy from water while minimizing turbulence and wear. Digital control systems adjust flow and rotational speed in real time, responding instantly to changes in demand or river conditions. Many facilities built decades ago now produce significantly more electricity than they did at commissioning, thanks to retrofits rather than new construction. One of the most important modern developments is pumped storage hydropower. These systems function as large-scale energy storage rather than simple generators. During periods of low demand or excess renewable production, water is pumped uphill into a reservoir. When demand rises, that water is released to generate electricity. As solar and wind power expand globally, pumped storage has become critical for grid stability, acting as a battery capable of storing energy for hours or even days. In many regions, hydropower is no longer just a power source. It is the backbone that keeps renewable heavy grids functioning. Hydropower has also diversified in scale. While megadams still exist, smaller projects have gained prominence. Run-of-river systems generate electricity without large reservoirs, reducing environmental disruption. Micro-hydropower installations supply remote communities with local, reliable energy, often replacing diesel generators. These smaller systems reflect a shift toward contextual solutions rather than one-size-fits-all infrastructure. Environmental refinement has become central to contemporary hydropower. Modern projects incorporate fish passages, sediment management strategies, and controlled flow regimes to better mimic natural river behavior. Environmental impact assessments are now standard, and in some regions, obsolete dams are being removed entirely to restore ecosystems. This represents a significant cultural change from dominating rivers to negotiating with them. Globally, hydropower remains the largest source of renewable electricity. Countries like China, Brazil, Canada, and Norway rely on it as a cornerstone of their energy mix. At the same time, developing nations in Africa and Southeast Asia view hydropower as a path to electrification and economic growth. Though projects are increasingly scrutinized for social and environmental consequences, Hydropower today occupies a complex position. It is mature but still evolving. It is clean but not impact-free. It is ancient in concept, yet modern in execution. Most importantly, it has shifted roles from primary driver of industrialization to stabilizing force within diverse, renewable energy systems. In this contemporary form, hydropower is no longer just about harnessing rivers. It is about balance between energy and ecology, infrastructure and community, reliability and responsibility. Flowing water still turns turbines, but now it does so as part of a carefully managed, globally interconnected energy future. The legacy of hydropower reaches far beyond electricity meters and dam walls. It represents one of humanity's longest-running partnerships with nature and energy relationship that began with wooden wheels in shallow streams and matured into continental-scale power systems. Few technologies can claim such continuity across millennia while remaining central to modern life. Hydropower fundamentally changed how societies understood energy. Long before fossil fuels dominated, it demonstrated that natural forces could be harnessed reliably and repeatedly. This idea shaped the Industrial Revolution, enabling early factories to operate continuously and predictably. When electricity arrived, hydropower proved that renewable energy could scale, delivering industrial-grade power without combustion. That lesson remains vital today. Economically, hydropower helped build nations. It powered heavy industry, enabled electrification, and supported regional development where other energy sources were impractical. Entire cities, industries, and transportation networks grew around hydroelectric projects. In many countries, hydropower became synonymous with modernization, stability, and national self-sufficiency. Technologically, the influence is equally deep. Turbine engineering, advanced fluid dynamics, materials science, and control systems that later influenced wind energy, aerospace, and mechanical design. Grid management techniques, especially rapid load balancing, were refined through hydropower long before modern smart grids existed. Even today, hydropower plants remain among the most responsive and durable components of electrical systems. Culturally and environmentally, the legacy is more complex. Large dams altered landscapes, displaced communities, and transformed ecosystems, forcing societies to confront the costs of progress. These consequences reshaped environmental law, public consultation, and infrastructure planning worldwide. Hydropower became one of the first technologies to teach humanity that energy decisions are never purely technical. They are social and ethical choices as well. Perhaps the most enduring legacy is perspective. Hydropower connects ancient ingenuity with modern responsibility. It reminds us that innovation often begins with simple observations, like water turning a wheel, but grows powerful when combined with science, planning, and restraint. As the world searches for sustainable energy solutions, hydropower stands as both precedent and guide. It shows what renewable energy can achieve at scale, and what must be considered when nature and technology intersect. From riverbanks to hydropower's legacy is written not only in watts, but in how humanity learned to work with the forces that surround it. The future of hydropower is less about building ever larger dams and more about intelligence, integration, and restraint. As global energy systems shift toward decarbonization, hydropower is poised to play a stabilizing role, quietly enabling other renewables rather than competing with them. One key trend is the expansion of pumped storage. Hydropower is large-scale energy storage, with solar and wind generation fluctuating by hour and season. Grids need dependable ways to store excess electricity and release it on demand. Pumped storage already provides the majority of the world's grid-scale energy storage, and new designs including closed-loop systems that are not connected to natural rivers promise lower environmental impact and greater siting flexibility. In the future, hydropower may be valued as much for when it generates power as for when it chooses not to. Will further reshape operations. Artificial intelligence and advanced sensors are being deployed to optimize turbine performance, predict maintenance needs, and manage water resources more precisely. Real-time data will allow operators to balance energy production with ecological requirements, adjusting flows to protect fish migration, sediment, transport, and downstream communities. Hydropower plants will increasingly function as adaptive systems rather than static. Infrastructure. Smaller-scale innovation is also accelerating. modular turbines, low-head systems, and in-pipe hydropower could unlock energy from existing canals, water treatment facilities, and irrigation networks without new dams. These approaches favor distributed generation, bringing clean power closer to where it is used while minimizing disruption to rivers. Climate change introduces both urgency and uncertainty. Shifting rainfall patterns, melting glaciers, and prolonged droughts will affect water availability in many regions. Future hydropower planning will need to incorporate climate resilience, diversifying sites, and integrating forecasting to manage variability. In some places, this may mean rethinking long-term reliance on single river systems. Beyond Earth, hydropower's principles may even inform off-planet engineering. Closed-loop, fluid systems and turbine dynamics are already influencing designs for energy and life support systems in extreme environments. While speculative, it underscores hydropower's enduring conceptual relevance. Ultimately, the future of hydropower will be defined by balance. Not domination of rivers, but cooperation with them. Not just megaprojects, but smart, context-sensitive solutions. As energy systems grow cleaner and more complex, hydropower's role will be to steady the flow, quietly turning motion into reliability for a world in transition. From simple wooden wheels turning beside ancient streams to towering dams and turbines powering entire nations, the story of hydropower is a story of continuity and transformation. Across centuries, humanity learned not just to use moving water, but to understand it, refining raw motion into mechanical work, and eventually into reliable, renewable electricity. Few energy sources can claim such deep historical roots while remaining so relevant to the modern world. Hydropower showed that renewable energy could operate at scale. Long before sustainability became a global priority, it powered early industry, electrified societies, and today supports cleaner, more flexible energy grids alongside wind and solar. At the same time, it taught hard lessons about environmental balance, responsibility, and long-term planning. As the world looks for stable solutions in an uncertain energy future, hydropower stands as both a foundation and a guide that progress can grow from ancient ideas when shaped by science and care. If this documentary helped you understand how water wheels became hydropower giants, please like the video, share it with others, comment your thoughts below, and subscribe for more deep stories on history, technology, and human innovation, because sometimes the future is powered by ideas as old as flowing water itself.